In this video, I'd like to talk a little bit about the rotation of Mercury and how it was discovered that it was rotating so slowly. So as we discussed in a previous video on the timing of Mercury, if this is the very top view of Mercury, maybe that's the North Pole, Mercury would be rotating something like this. And as we discussed, it takes something like 59 days for Mercury to make one rotation. So if there was some feature on Mercury, say like this dot here, it would take 59 days for this dot to go all the way around. In other words, this rotation here is obviously quite slow. So if you're an astronomer trying to watch Mercury, it's very difficult to get a handle on this because the rotation is just so slow. There wasn't any features to track. It always kind of looked the same. It's like maybe Mercury isn't even rotating. It just wasn't clear what was going on. So I'd like to just tell you how the rotation of Mercury was discovered. And the way it was discovered was very clever. It was done by using something called the Doppler effect. So let me tell you what the Doppler effect is about. So the Doppler effect in a nutshell is about waves. And I'm going to show you sort of how it works with the waves now. So what I have up here is, let me just let it reset itself here, is I have a source S and an observer O. Okay, so that's probably the very first important thing to remember about the Doppler effect, is that there's sort of an observer and a listener here. So the S here in our simulation is going to be the source of waves. And the observer, looks like a big O here, but let's just say this is the observer. This is going to be who's listening to the waves. Could be your ear or the reception or whatever it is, whoever is sort of receiving the waves. And the type of waves that we're talking about here can be just about anything here. It definitely works for sound waves. If you ever hear an ambulance go by, you can hear the frequency shift as it goes by. And it can also work for light waves, and this is how astronomers used it to measure that rotation speed of Mercury, using light waves, or in this case, radio waves, as we discussed. But it doesn't really matter what type of wave it applies to, so long as you remember that whether it's a sound wave or a light wave, the wave always has the properties of some amplitude going up and down like this. And I hope you remember from our lesson on waves that the distance between any two crests is the wavelength like that. And the rate at which a little part of the wave goes up and down like that is called the frequency f. So I hope you remember all that stuff. So keep that in mind. And also the two definitions I just put out, that for the Doppler effect, there's always going to be a source of waves, something that's generating the waves, and an observer, something that's ultimately receiving or listening to the waves. Okay, so back to the simulation then. Here I have a source of waves right here, and here I have an observer of waves right here. Okay, so what I'm going to do is I'm going to start the emission by clicking this button up here. And what they mean by emission is start the emission of the wave. So if I do that, you see the waves coming out of the source. Okay, so they look like just a bunch of concentric circles. But if you want to think of them as waves like this, let me show it down so I can tell you. Maybe we can pause it for a minute. You can think of this white space here sort of as the wave going down. It leads into one of these solid lines which is going up, and then a white space where it's going down, and a line where it's going up, something like that. So you can sort of think of the wave that way. Maybe it'd be nicer if these lines were a bit thicker here, but that's sort of where the wave is that we're talking about. And so back sort of to the diagram here, I just want to make sure you know what we're talking about here. When we have the source putting out those waves, like a wave here and a wave here, maybe let me draw one more in there, you can definitely think of the waves as sort of going down and up on the white thing, and then down and up and down and up. That would be just fine like that. So that's the wave that we're talking about, going out like that. And they sort of exist in all directions, sort of related to those white things. And so that's sort of how the source S is sending waves out in all directions. Okay, so the question now that becomes is, what is the observer over here going to receive? So as I just turn it on again, you can see that basically what happens is maybe what you would guess is the observer receives nothing more than the wave pattern that the source has put out. So as the lines leave the source and travel out, you can see that the dark lines eventually hit the observer and hit the observer and hit the observer, and that's sort of what you see. And if you look up at the chart up here, it's very nice. You can see now it really looks like a wave as emitted by the source. This is what's coming out of the source. And you can see these are the waves as detected by the observer. This is sort of what the observer is seeing. So see, it's really no big deal. The source emits waves, the observer detects waves, and everyone's kind of happy. Okay, so that's sort of the setup. So what I'm going to do in the next video is show you what the Doppler effect is all about. And the way I'm going to do that is I'm going to use my mouse and I'm going to hold on to this source. I'm going to click and drag it, and I'm going to shove it towards the observer while it emits its waves. Then I'm going to grab it and shove it away from the observer while it emits its waves, and we'll see what happens. So next video for that.